And I'm going to have to apologize up front because I have way too many slides here. But the main takeaways that I want to get to is that as you see that tripolar sensor, we get improved signal-noise ratio with it, the spatial resolution is increased, and we also see high-frequency activity that you normally don't see with regular EEG. And because of the increased signal and noise, we typically take about 1/10 the number of stimuli when you're using event-related potential type things. And there was a wonderful, wonderful researcher, Helmholtz, who said, if you can detect signals from a certain point, you can inject signals to generate the same potential. And so why just sense? We also use the same electrodes to focus where our stimulation goes. And we found that we can decrease glutamate, increase GABA. Oh, if you saw the plenary presentation this morning, he was talking about GABA, injecting GABA. But we found a way that we can increase the GABA with the stimulation. No pain and sensation, and this diazepam works in the GABA channels, and so we actually enhance that. And these are just some of the areas that it's worked for stopping status epilepticus, which is continuous ongoing seizures that in the U.S., approximately 20 to 40,000 people die each year from that. And we've prevented brains from becoming epileptic. And then we've recently jumped into a Parkinson's model and showed that it works there as well, and that it actually blocks the pain by working on the opioid receptors. So we have to have a little, I think I must have went too far. Okay, so a little math here. If you look at these as electrodes on the scalp and you're getting potentials from them, V1 minus V0 and then V3 minus V0 gives you two differences in the x-axis. V2 minus V0, V4 minus V0 gives you two differences in the y-axis, and so that's the second spatial derivative, which is the Laplacian. So if you Taylor series expansion on those points works out to this, where the higher order area here is of the R squared for the first term of the higher order. If you rotate those electrodes around infinitesimally small amount, 360 degrees, you end up with a ring and a disc, bipolar, which is significantly better than just using disc electrodes, but you can't get a PhD doing that when somebody's already done that. So if you add more electrodes and get another difference on that, then it's more complicated. And we see that the higher order terms here, truncation terms, are of the fourth order, which gets us closer to the Laplacian than the single ring. And so if you rotate those around, you end up with two rings and a disc. And doing that Taylor series expansion, we found after canceling terms, it's 16 times the middle ring minus disc minus the outer ring minus disc. So it's a weighted sum where this inner part is weighted 16 times what it is. So if you saw those rings and think about paste, okay, so Voikin was moving us forward, and all of my colleagues are telling me, you're taking us back in history 10 years. Nobody uses paste now, Walt, but in the clinic they still do, and if you want the best signals, that's what you have to deal with, is this paste. And so if you think about conductive paste, it's used to make contact with the skin. Try to make good contact with the skin. Well, what happens when you put it on those electrodes? Is it going to short them out? Well, that's the first question I always get. Why doesn't it short them out? And so, this is taking a model of the electrode-electrolyte interface, and also what the speaker this morning was talking about helps us get rid of this. That's pretty cool. I'd like to figure out how to do that. But if you think about this, it's partially shorting these. And so what we did was do the impedance spectroscopy over frequency and measuring impedance to try to see what happens. And so what we really want to be able to do is keep that impedance between the rings high, but impedance going between the electrodes to the skin low. So we have to do some adjustments, I guess you would say, with the size of the rings to get this type of stuff to happen. And so what we're seeing is that we want the impedance to be high between our rings. And so we're starting out here quite high, and then as we get into the higher end, it's lower impedance there. And if you think about that paste, okay, it's doing the same thing to us here, so that as we get up into these higher areas of frequency, the impedance to the skin is being lowered as well. Okay. So then this is the model that we came up with, where we're using these constant phase elements to match our empirical data for the electrode-electrolyte interface here. That was just, that should be 2017, not 2007. Sorry about that. Okay, so moving on a little bit to understand more, we did some computer modeling where these are concentric spheres with conductivity of the brain, the cerebral spinal fluid, skull, and scalp, 2 disc electrodes. Dipole was put here in the center, and we're calculating where the magnitude of the electric field is half of the maximum. And so this shaded area here is where that is for the disc electrodes, same for tripolar. And we found that this was about 11 times less than this area here. So they're more spatially selective. And in doing experiments, we put 35 electrodes on the left hemisphere and had people click a switch, synchronized the EEG recorded here with the switch enclosure to ensemble average. And at the CZ location, this is what we saw with regular electrodes, with the bipolar electrode, and then with the tripolar electrode. And you likely know that if you put regular electrodes any closer than 3 to 4 centimeters apart, they see the same thing. And that's what you're seeing over here. Those 35 disc electrodes, the signal looks nearly the same. And for the tripolar electrodes, the morphology, the shape of the signals is pretty much different in every single location. So with the tripolars, we can put them right side by side. Using those signals, we calculated the average signal-noise ratio, and found with tripolar we had about 4 times better than the disc and about 2 times better than bipolar. So a lot of times people are asking, why go through the complication of adding a second ring to do tripolar? Bipolar is so much better. But it was significantly better. And this mutual information were about 11 times better and about 3 times better. So it's more focal, basically. It only sees what's directly below it. So here, if I'm lucky, I'm going to show you a video that I should have known. It works on the computer, but it doesn't work on the projector. So after the presentation, if you'd like to see the videos, I can show them to you. So the other part of the talk was about auditory brainstem response. Many times people say, well, it's Laplacian, so it's a shallow, picking up things from shallow sources. Brainstem, I would argue, is a little deeper than shallow. And so what we found was that by giving clicks within 100 stimuli, we've got fully shaped auditory brainstem response with tripolar electrodes, but with regular electrodes. You might argue that that's the wave 5 there. I'd probably agree with you, but there's hardly anything else showing up. And typically it takes 1,000 to 2,000 stimuli with the EEG to get the good signals that we pick up with just 100. And we've done brain-computer interfacing work offline and got about 80% correct single event thinking left or thinking right compared to the disk with 65%. But that doesn't do us much good for people. You need to do real time. And so we put together a way of detecting, determining which electrode, which location, which frequency to use to get their imagined movements. And this video probably isn't going to work either. Oh, it is. Okay, that's odd. So there's going to be a target popping up on the right here, then the ball, and he's got to think about moving that ball to hit the target. These are the tripolar electrodes on this side and the other going into this preamplifier and then into the amplifier. Target on the left, and he's thinking about moving it over and hit it. Target on the right, and he hits it. Okay, and so all that black stuff is muscle artifact. Those aren't the brain waves, and these are bipolar signals here. With regular electrodes, typically you take bipolar difference to try to cancel out common signals, such as muscle artifact. But you can see that that doesn't happen. And this is one of our sensors right next to this, and you can see the brain waves underneath there. And if this demo works, I can't tell if it's running or not. And I can't control it here. So, yeah, it is going. Okay. So in just a second here, she's going to turn her head, and we've got the electrodes on the back of her head here, where there's a lot of large muscles. And so as she turns her head, she's going to have her eyes closed, and the bottom 6 are the EEG signals, the top 6 are the tripolar output. So there's her head turn. You can see all the muscle artifact in the bottom signals. It's hard to tell, but there's alpha waves up here. It's not hard to tell now. I mean, if you understand, if you've ever seen alpha waves, you can see that they're still there. Down here, you can't see them though, right? So this is a simplification of how it works. So if you think about a pond or pool of water and a breeze blowing, you see ripples on the water. And if you take an inner tube, put that on the water, inside it's flat like ice or glass. And so inside this is our outer ring of the tripolar electrode. Inside is where our middle ring and center disk is. So this is acting like a shield from the global noise radially coming in. And then we've got a clean area here to see what's going on below. And then this is a pretty crude figure. My drawing isn't very good, but this is the outer ring and center disk difference that goes into a difference amp. And the common signal on here, if you can see the sine wave, that's common to both of them gets canceled, and all you see is the square wave. Same kind of thing happening down here. And so signals that are coming from far away, such as AC mains, or if you're trying to get signals from the brain, signals coming from muscles, generate nearly the same potential on those tripolar electrodes because they're only a millimeter apart. And so then when you take the difference of that, that cancels out. And you're left with the signals that are directly below. And so this just shows how steep the roll-off is, and I'm running out of time. So this is onset of a couple, of seizures, bipolar electrodes. These are our tripolars right at the onset of seizures and how much cleaner they are compared to these. This is the onset of a seizure in another patient. These are bipolar signals as well. You can kind of see that there's some kind of wave under there, but it's all that muscle artifact. And so with this, no signal processing. It's just the sensor, the tripolar sensor, and taking that difference that cancels that muscle artifact out. In 14 patients we've recorded that have had seizures where we've recorded the EEG and the tripolar EEG at the same time, we've been able to see something here that I'm going to show you about that this is a bipolar EEG, generalized seizure here, partial seizure here. Partial means that it's electrical activity going on, but they're not moving yet. This is what the epileptologists call a seizure. You know, for them, it's a clinical seizure where they're moving. This is just time frequency representation where time is going this way, frequency increasing, and the power, the higher the power, the lighter the color. So you can see during the seizure here, it really gets, when there's a lot of muscle artifact, it really gets increased in the brain activity in there. But what I want you to really focus on is this black ellipse here. You can see these little pulses that are happening about 3 minutes before the partial seizure. You know, that's what we've been seeing in every patient that we recorded, sometimes out to an hour before in the area that tells us where this is happening. This is another one, but the power is dark here when it's increased. Same thing happening here in the regular EEG, bipolar EEG, then our tripolar here. If we expand that little area, we don't see anything in the spectrogram for the EEG, but in the tripolar, you can see these pulses showing up. And if you keep expanding, you can see what people are calling high frequency oscillations now. And we've taken and made real head models from MRIs of our patients and used back propagation and forward modeling to determine where the source is coming from for our potentials. And I've got a little video here of a couple hundred milliseconds, and we'll see, yes, it's going to run. So you can see we're localizing this high frequency oscillation to the visual cortex, left visual cortex. This one doesn't localize as good. This one reminds me of a lightning storm. But this is the area where it's really originating. And then just trying to localize some actual hand movements, physical hand movements. And so right hand here, and we can see in the tripolar that this is the C3 location, but we're also getting some high frequency activity up here around 80 hertz. Regular electrodes here, it's hard to pick out which one you would want to use. Left hand in this case, and we're still seeing some higher frequency activity up here as well that's not seen in the regular EEG. But we should talk a little about the stimulation as well. And this just shows computer modeling using that concentric sphere, same model, how focal it is, where it's white is the area that would be activated in the brain from the tripolar stimulation. This is from regular electrodes, and so most of the brain would be active. And I'm going to skip over all of our safety testing just to get to, this is a model of status epilepticus, and in this, turn the stimulation on here, and 1 minute of stimulation stopped it. 2 hours later, it still stopped, even with the convulsants in. And this was non-invasive. Same thing for a second model and a third model. And this shows our automated seizure control system for rats. Not that we really need to save rat lives, but I had to start somewhere. And this is a control. In this one, it automatically turned the stimulation on once, and that stopped the seizure. And then in another group, it took 2 doses of stimulation. And it protected the brain. Like I said, it increases GABA, decreases glutamate. In epilepsy, that works out perfect because there's too much excitatory glutamate, not enough inhibitory GABA. And in status epilepticus, it did the same. And this one is protecting the brain from becoming epileptic. And so in controls, within 25 days, they were all epileptic. But in these ones that we stimulated 2 minutes each day, it protected the brain, turned the stimulation off outside, keep stimulating inside the brain. It protected it 20 more days and 50 days before that. And then in that Parkinson's model, we found that it affected multiple neurotransmitters and other things protecting the brain even after 20 days. And so that finishes it. So basically, I already told you all of those, and it's taken a lot of people to help me. And some of the people that are using our systems brings us to their